So the next thing we should really cover is the associativity of composition. This is a really important feature of composition, but it's not quite as important to see the proof as the other things. So I'm going to make that part of the bonus material at the end, sort of following the policy I established last time that I'm going to do all of the most important things at the beginning and then tell you when you could stop watching safely if you wanted to. Okay, so for now, at least until we get to looking at how to prove it at the end, you can accept this theorem that, and I hope you accept also that it's not obvious. These two things, if you compose three things in different orders, sort of, if you compose these two first and then compose it with the third, versus if you compose these two and compose it with the third in these different orders, then you would get different, you would describe those in different ways, right? The description of these following the definitions are two different descriptions, and at first glance they might or might not lead to equal sets, and yet they do end up leading to equal sets. So this is a theorem that needs proof. Notice that everything is kept in the same order, so we're not saying you can change the order in which things are composed. I mean, it's sort of a changing the order. Well, it's changing whether you compose these first and then this with them, or these first and then this with them. But it's not moving, it's not changing the order in which S, T, and U show up. So for example, if I swapped T and U, that would change things. So what I'm trying to say is A composed with B is not the same as B composed with A, usually. You would not expect that to be the case usually. So composition is associative, but not commutative. By the way, this is pretty commonly used terminology in math, associativity and commutativity. You've seen it back here in Theorem 29, we were talking about these set operations. So like this is associativity of intersection, that you can regroup, so you can do that with composition. But commutativity, you have that for intersection and union. You definitely do not have that for composition. All right, proof later. Moving on, Theorem 62. So here we're going to look at domain and range for composites. And this is, so part 2 is easier to read to start with. So this is telling us about the range of a composite, that the range of a composite is a subset of the range of the left-hand thing. Similarly, the domain of a composite ends up being a subset of the range of the right-hand thing, but it turns out we'll actually be more interested in the situation where you have equality of the domains, and to get equality of the domains you need this extra assumption. Okay, so don't worry yet, we're going to dive into all of this and see exactly why you need the extra assumption. But I just want to point out that this is basically, these are kind of facts that we took for granted or assumed or determined very quickly in order to draw these pictures. So here we were in a setting, where is it? We were in a setting where T was a subset of X product U, and S was a subset of U product A, right? So the domain of T was big X, the range of S was big A, right? So here were our pictures. The domain of T was big X, the range of S was big A. Sorry, the range of S is not big A. The range of S is a subset of big A, right? Yeah, just from knowing this, you don't know equalities. You know what's a subset of what. So this tells you that the domain of T will be a subset of X, and the range of S is a subset of A. I shouldn't have said that they're equal. It turns out, in the particular example, the domain of T equals X, but the range of S is merely a subset of A. Okay, anyway, we sort of took for granted, or verified very quickly by inspection rather than actually proving, that when you compose them and you look at S circle T, S composed with T, that the domain of that will be the same as the domain of S, so X, and that the range of it will be a subset of the range of, sorry, the domain of it See, this is the left-right mix-up. The notation is just so flipped around from what you expect usually. So we drew an X on the left and an A on the right. This reflects that we understood that the domain of this composite is contained in the domain of the right-hand side, and the range is contained in the range of the left side, which in the drawing, the right side here shows up on the left and the left side shows up on the right. Okay, so all I'm trying to say is that this is a fact that we already incorporated into our picture. Now we're going to prove it. Okay, here are the statements, and I'm just going to focus on this one, the second one first, because it's kind of simpler, and the ideas in here will be contained in the other one. So better to do the simpler one first. So this is an inclusion statement, a subset statement. So we'll start as usual. Consider any, what should we call it? So I could say Z, but maybe I can use a letter that feels better. If I follow the naming convention that I was using here, then the kinds of things that I expect to wind up in the range of this composite are the kinds of things that will end up over here, so maybe in big A. So things with letter names like A, B, C, D. So how about A? Just so it's easier to compare ideas with that picture. So consider any A in the range of S composed with T. So here A could refer to any of these if this picture applied. But of course, right now, S and T could be any sets. They don't have to be those finite sets that we wrote out in that example. These really could be any sets. Okay, now to do anything with this, I should unpack using the definition of range. So that means there exists, so A is the second position in a pair, so there exists a first position such that the pair is in this thing, right? So we can get, let's call it X, such that X, comma A is in there. That's from the definition of range, right? So this is the existential instantiation. I skipped that step where I use axiom 5 to write down the full existentially quantified statement. So I just went right to the existential instantiation like we often do. And then now here, I need to break down what this means. So let me just break it down. So this is sort of using axiom 5 and essence of pairs. So to fully see where this is coming from, you have to use the non-shorthand, the full definition. So this here is written in a shorthand. You'd have to use the non-shorthand with axiom 5. But where you end up is where it looks like you would end up, which is the following. There is some, and what should we call our middleman? Let's call it U. There is some U such that X comma U is in T, and U comma A is in S. So now existential instantiation. We can get U such that, and then let me be a little bit lazy. Do that. And as you might expect, people don't usually write this sentence. They'll just go right to the existential instantiation. So I'm just going to delete it. And you can feel free to skip that sentence normally. So this pair is in the composite, therefore we can get a middleman. That's what it achieves. And typically in a sentence like this, we wouldn't just stick a logical symbol, we would write English. All right, so I feel like I've unpacked where I started from as much as possible. I don't have any more information about T or S so that I can unpack what it means for these to be elements of T or S. So time to focus on the goal. What was the goal? Was to show that this A, which is in here, is actually in here. So I want to show that A is the second position of a pair which is in S. Oh, I'm done. There it is. So that's pretty nice. Since UA is in S, now existential generalization, we have A is in the range of S. Because we have found something such that that something comma A in a pair is in S. So that's it for the second part of Theorem 62. So the range of a composite is a subset of the range of the left-hand thing, which I always think of the left-hand thing in the composite as actually being the second thing. So the composition, if you look at the picture, when I look at S composed with T, I think of it as following the edges of T, following the arrows of T, and then following the arrows of S. So T, then S. So the range of that, the range of S composed with T, will be a subset of the range of the second thing, which is the one on the left, confusingly. All right, now let's focus on this theorem. This theorem is really similar, actually. If you look at the conclusion, it's just a domain rather than range version of things. So it's saying that the domain is going to be related, the domain of the composite is going to be related to the domain of the first thing. Except this one is trying to give us an equality. Well, okay, let's start the proof. So we need to assume the hypothesis first. So assume range T, subset domain S. And right now this looks like it's coming out of nowhere, but just hold up. You'll see where it ends up being useful. So just assume it. Don't think about it yet. Then we're trying to prove this. So the proof will split into two portions. Since I'm proving an equality, there are two inclusions, right? So for the forward inclusion, it's actually going to be a really similar argument to what's going on in here. So let me just do that quickly, and then the other inclusion is going to be the interesting one. So let's do this one quickly. So consider any x in the left-hand side, domain of S composed with T. Now I use the definition of domain. We can get some y, maybe I won't call it y, let me call it a in this case. We can get some a such that the pair x comma a is in S composed with T. Now let me use the definition of composition, another existential instantiation. That means I can get a middleman. So we can get a u such that xu, let me make my a's and u's clearly distinguishable, so it shows that xu is in T and ua is in S. And then what was my goal was to show that this x that I started with is actually in the domain of T. But look at that. So since the pair xu is in T, x is in the domain of T. That's the existential generalization. We found a u that works. So that, well, I shouldn't put the box yet. We have the other inclusion to do. Okay, so this is going to be the interesting one. So let's see, consider any, and then what should I call this? I'm going to call it x again. X in the domain of T. Well, I do have a way of kind of unpacking that a little bit. Then we can get a u such that x comma u is in T. And you know, it doesn't really matter what letters you pick. Like, it's totally fine to say we can get a y such that x comma y is in T. But I'm trying to pick letters that to help me keep track of things. I'm trying to pick letters that go with my mental image that I have from the picture here. Since this is so fresh in my mind, I think of XYZ type stuff as being over here, UVW type stuff as being the sort of middle guys, and ABC type stuff as being over here. But this picture is no longer applying at all, right? Like, this is a general setting. Just helps keep track of things. Okay, so we can get a U such that the pair XU is in T. Now, I've actually unpacked what I have to the greatest extent that I can, except I never used this assumption, so somewhere that's going to come in. Let's think about our goal at this point. So, goal thinking area here. So the goal is to prove that X is in there, right? X is in the domain of S composed with T. That's the goal. So in other words, we're trying to do an existential generalization, right? We're trying to find is the key verb there. We're trying to find a, what to call it, an A such that the pair X comma A is in S composed T, right? That's how you show something is in the domain of something. Just find a possible second position in a pair which is an element of the thing whose domain you're interested in. So that's our goal. Okay, but this statement here can be broken down, right? This breaks down to saying there exists some U, but let me not confuse it with the U back here. I don't know that it'll be the same one yet. Let's call it V. There exists some V, middleman, such that X, the pair XV is in T, and the pair VA is in S. So that's how that breaks down. So my goal is to find an A such that there's a V such that XV is in T and VA is in S. So let me say that again. My goal is to find an A such that there's a V such that the pair XV is in T and VA is in S. What might work as a V, now staring at what we have? Probably U itself, right? That seems like the only thing that has hope here of working as a V. So here I suspect that U would make a good V. A good choice of what V should be. So once I start thinking that way, then my goal is to find an A such that the pair U will play the role of V, U comma A is in S. So want to find A such that the pair U comma A is in S. Is that possible? So I've got this U here. I have no control over the U, right? I got the U purely from the knowledge that X is in the domain of T. So purely from the knowledge that there exists a U such that this pair is in T. So the U is sort of out of my hands. It's out of my control what it is. It's granted to me by the powers of existential instantiation. So then, should there be an A such that the pair UA is in S? Should there exist an A? I don't see why, except if we have this assumption. So you see where this assumption is needed. So, okay, but that's not totally clear. So what does this assumption actually enable? It tells us that things that are in the range of T are in the domain of S. For there to exist an A such that UA pair is in S, we need to know that U is in the domain. So here, to achieve this goal, we need U in the domain of S. then there will exist an A, right? This assumption tells us that in order to get U in the domain of S, it's sufficient to know that U is in the range of T. But we have this. That tells us that U is in the range of T. So now we can finish the argument, now that there's a nice plan. So then U is in the range of T. That's existential generalization from here. So since the range of T was assumed to be a subset of the domain of S, universal instantiation on this universal, U is in the domain of S. Therefore, we can get an A such that the pair U, comma A is in S. That's using the definition of domain, existential instantiation. Now, since XU is in T and UA is in S, we have found a middleman, U, joining X and A here. So we have met the conditions needed to have the pair XA be in the composition. We have the pair XA being an S composed with T, written in that order. Thus, what we actually wanted is X is in the domain of T. X is in the domain of T, since we found an A here that works. Okay, now we can put the bunks. All right, so we've proven the theorem. In the bonus content at the end, I'm going to show you something that is part of a good habit when you're reading through theorems, which is looking at why assumptions are needed. So could we have proven this without having this assumption here? Could we have just directly proven this? Now you can see from the steps of the proof that we needed to use the assumption. So that's a good sign that the assumption is needed. But an even better sign that the assumption is needed would be a counterexample. So an example of a situation where we manage to we do actually have this inclusion, but we just don't have this one. So we can look at a counterexample at the end after I finish the core important parts of the lecture.